The other concept that we're going to get to towards the end of this course is we're going to talk about area and integral calculus. Many quantities in physics, for example, quantities of work may be interpreted as the area under a curve. So this leads us to ask the question, how can we find the area between the graph of a function and the x-axis over an interval? So again, here's our curve, our function, and we want to know what this area is between two values. Okay, let's talk about the area problem and approximate the area under f of x equals x squared from 0 to 1. So here's our area under the curve from 0 to 1. As you can see, of x squared, if you put 0 in, you get 0, 0, right? If I put 1 in, I get 1, and then we have all these values in between. All right? From 0 to 1. Well, what if we draw some rectangles? We know how to find the area of a rectangle. Correct area equals base times height, base times height. So we could approximate all of these rectangles. We could add them all up, and we would get a sum of the areas. Now, how accurate is that? Well, you can see it would be a little more than the actual area that's shaded. Here we can do a less. As you can see, here's bigger rectangles, which would be not as accurate as the smaller rectangles. And then the more rectangles, as you can see, the more rectangles we put in here, the better the approximation of the actual area we're looking for would be. So the more rectangles, the better the approximation. So let's look at this. Here's the one with 4 rectangles. The sum of the areas of the rectangles overestimates the area under the curve. Well, that's pretty obvious just looking at it. It would give us an estimate, but we would know it's a little too much, as you can see. But what if we put more rectangles? So if we continue this process of dividing the interval from 0 to 1 to more and more rectangles, then the sum of the areas of the rectangles becomes closer to that exact area. For every rectangle we add, if we increase the number of rectangles, hypothetically to infinity, then the sum of the rectangles would give the exact area. Below the number of rectangles is 10, 20, 50, and 100. And the exact answer we are approaching is 1/3. So as you can see, as we get infinitely, we still have a little bit, but if we could go to infinity, which theoretically it would be exactly 1/3. So the smaller and smaller and smaller those rectangles get, the closer we would get to the area in the curve. And we'll get to this more when we work in the later sections when we start talking about integration and the sums. We'll do a little bit now, but more later. Okay. Other aspects of calculus. So suppose we want to determine the velocity of a rock fired from a catapult at a given time, or an airplane moving in 3 dimensions. We might want to graph real value functions of 2 variables, or determine the volume of solids of the type shown in the figure below. These are only a few of the types of questions that can be asked and answered using multivariable calculus. However, before exploring these and other ideas, we have to get a good foundation first. So we're going to look at the study of calculus in one variable by exploring the concept of a limit. So it's important to get this concept of a limit down before we can get into some multivariable calculus, which will be later on in your if you plan on taking more calculus.